Okay, in this lecture, we are going to look at, we basically are going to revise the particle image velocimetry and give also some examples. These are not lab demonstrations, but these are examples from my research work as well as from the research work that is happening in NAL. So the lecture notes partly are courtesy of Dr. L. Venkatkrishnan of CSIR NAL. And so let us look at let us do a quick recap of what we taught in the last few lectures. As we can see that we covered all these things, that recording techniques, stereo PIV. We did not cover tomo PIV though. Then processing techniques, that how you can do what is correlation, what is Fourier method, and post processing techniques also. Um, we're going to talk a little bit about the uncertainty in the PIV measurements in this particular lecture as well. So, if you recall, if you have to summarize, PIV, we first have to look into the challenges of experimental fluid dynamics. That is, for example, this is a flow behind a bluff body, where you can see this flow is very intricate. We can see there are lots of small scale structures, large scale structures, lot of twists and turns in the flow. So the idea is that if you have to really do the measurement properly, you have to accurately measure the velocity, the strain, the density, and the pressure. And this is the challenge in experimental fluid dynamics. That means you need to resolve these measurements. So that our answer was particle image velocimetry, which is an optical technique, as we know by now, which does not interfere with the flow at all, unlike probe-based measurements. And if you do, at least even low-speed PIV, you can get an idea of the spatial structures that are there in the flow, and therefore it is very quantitative in nature, and it is also very visual. So the visual representation actually, enables us to uh, have insights into the flow field, at least look at the spatial structures. High-speed PIV will enable you to resolve both the spatial as well as the technical, as well as the temporal structures. But unlike, for example, LDV, the temporal resolution may not be very high. Depends on the kind of camera and the laser that you have. Okay, so the idea was very simple, that if there is a displacement, say for of a fluid parcel, this is optical velocimetry essentially, and if you can calculate the distance that it has traveled or the displacement that it has suffered in time delta t, and the x component of the velocity in this case will be the displacement in the x direction divided by the time interval that has elapsed. So basically you wait with a watch and take two images. That is, in a very nutshell, the very basic premise of velocimetry. Of course, we showed that we do it by using a laser sheet, which has got a finite width, by the way. And the particles which are there within this laser sheet, this has got a finite thickness, or within the plane of the laser sheet, those are the particles which are only visualized. So you can understand. So it is the same thing. The particles are moving, different particles are moving in this laser sheet, but these particles are only visualized inside this laser sheet. Whatever is outside, and we have spent a lot of time to say how out of the plane component motion can actually lead to errors in the measurement, even in 2D measurements. Okay. So these are basically the tracers. We already talked a lot about tracers and how they should faithfully follow the flow field and what are the kind of systems that are there. So you visualize those particles which are there inside this laser sheet. That's why you have those yellow dots over there. So the idea is that using a lens and a camera assembly, you record the positions of the particles, kind of, and this is a seeded flow. We assume that the seeded particles, follow the flow field quite faithfully, and then you can measure within that time interval. Okay, what is the velocity? So this is like an integral way, and this is how you measure the spatial velocity, spatial or the temporal velocity. Okay, so this is how the measurements are performed. This is very simple principle of the PIV technique. So you have to summarize in this way. You have what we have used a double pulsed laser, which has got a finite delta t between the two pulses. remember that this delta t between the two pulses are kind of controllable. Okay, so the laser, if you look at these laser pulses have a finite time span. Okay, so these are typically of the order of nanoseconds, and but there is a pulse to pulse separation which can be of the order of microseconds. Okay, and we can go even lower than that with these days. So we have already shown by using a cylindrical lens or a combination of concave, cylindrical, and spherical lenses, you create a measurement volume, which is basically a light sheet. And this is the area that is illuminated. Now we divide the area into multiple interrogation windows that we see over here. This is what we call measurement volume. And this is the measurement, this is the interrogation area, what we image on the imaging plane, which is typically a CCD. So the flow is seeded with particles. You image it. So this is the object distance, this is the image distance, this is the target. So once it is imaged, then you get two frames. It is a double exposure or two frames or double frame. This is a cross correlation CCD camera. So the image from pulse 1 and for pulse 2 are recorded, and you take out these interrogation windows. You have the intensities, okay, and you also have the displacement inbuilt because the particles have moved during this delta t time. And this delta t time is chosen such a way that particle has some finite displacement. Too small a delta t may not lead to any tangible displacement at all. So you need to have some idea about the flow field to choose this delta t. You cannot go completely blind. So you need to have an idea whether the flow is like 50 meter per second or 100 meter per second, and accordingly adjust this delta t so that you know what is the kind of displacement we are looking at. So these are the two these are the particle images. You take out the interrogation windows. This has got an intensity which is I1 and this is an intensity I2. The particles may have moved by a distance delta x. Then you do the correlation, which is typically done using Fourier transform. And then you get velocity vectors. You get one velocity vector for each window, for each of these measurement windows. So the idea is the ensemble of particles in these measurement windows basically move as a unit. They actually have the same velocity. Okay, and that is what is done by the correlation. So it finds out the most probable velocity essentially, or it basically maximum velocity or maximum displacement by minimizing, or the most probable displacement, okay, by maximizing the correlation. So the idea is that it involves rather a fifth step, which is the first four steps. First two are basically the hardwares, and then you have the third step, which is basically triggering. So triggering is also very important because when the laser shines, the camera should be ready to take the image. And then you do processing and post-processing algorithms, and you can find out different things. Once you get the vector field, you can find out vorticity, you can do averages, you can find streamlines, you can do lots of stuff. So these things are already covered in details. But this is in a bird's eye view of what happens in a nutshell in a PIV. So the methods of PIV, processing of PIV are many. So you have the statistical methods, you have the Fourier methods, you have the optical methods, all of which we have covered in details. Okay, so the idea was basically, if you have to summarize it very crudely, you set up a cost function, okay, between fx and gx, where gx is fx minus s, and the function usually represents, this fx represents a small block or a window in a larger image, basically the interrogation window size. So the match is obtained for the value of s, for this value of s that maximizes this cost function c. So that is like a most probable. Okay, so we try to match for what value of s this is maximized, c is maximized. Okay, and the function f, we have already seen what that function is. It consists of a point spread function, the geometric image, and all those things are embedded in this function. And we just have it represents a small block or a window in a larger image because it's an ensemble. Remember, we are trying to do a pattern match because you cannot track individual particles. So therefore, you are doing a pattern match between the two images. And this is how the correlation actually works. So this is fu, this is g minus g x minus u, and then you kind of get the correlation function. The cross correlation, how do you do it in a FFT? You basically transform the first exposure, okay, which gives you the first power spectral, and then you transform the second exposure, which has a displacement of delta x and delta y. If you look at it, this is the image, and then there is a delta function, and then the correlation result is G, which is basically the basically this, as you can see over here, and ultimately you get a correlation peak, okay, because you remember the Wiener theorem, okay, that we have covered in kind of details. That this is how it happens in the Fourier space, essentially. All right, so this shows actually a displacement, and that displacement d is actually what is the or the peak is at a displaced location d, and that gives you the number of pixels that the velocity at the displacement vector in terms of pixels. So this is the direct approach correlation. In that this we also covered, that there is a 4 pixel by 4 pixel template, and then there is a larger 8 pixel by 8 pixel sample. So you do this between image I1 and I prime. We already have done this. This is the shift. You are basically shifting this template all over, and this gives rise to a 5 by 5 pixel correlation. This we know it is 2m plus 1 and 2n plus 1. So this is how the correlation actually happens. This is a direct approach. The Fourier approach will be that you take the two images, you do the real to complex Fourier transform, and then you multiply the complex conjugate like this. This will give you, and then you do a complex to real inverse Fourier transform, and then you get the correlation data. So this is the way that most of the fast Fourier transforms actually work. So, okay, so there is a direct approach, and then there is an indirect approach. So indirect approach involves you to do an FFT, and then involves you to do a conjugate multiplication, and then an inverse Fourier transform. So if you want to, do the velocity determination, what happens is that you take these two images, and the output is that bright spot, which is the correlation. So and this will be located at a distance of d, which is that, okay. So it is the same way. So you take the two images, you do the interrogation windows, then you do the Fourier transform of these windows, and actually you do it for all. And for one such ensemble, if you do the power spectral, and then if you do the inverse Fourier transform, you will get a displacement which will shift this peak, okay, at a distance of d. So this will be at a distance of d from the center. As a result of that displacement dp is actually where this bright spot will come, which is basically this peak. If you look at it from the top, it will resemble a bright spot, and then there will be noise. Okay, so if you search the peak, this will be the peak, which will be a single bright spot, and then there will be a background noise, which is basically due to the other terms. Okay, but this is the peak, which is supposed to be at least 2-3 times higher. This will represent as a bright spot, and the distance of the bright spot from the center is going to give you the displacement. So the peak will be located at a distance d. So even for small displacement, this can be measured, and then there is no directional ambiguity. Okay, so it can be located from the center anywhere. Okay, anywhere in this plane. So you can also know the direction. That means you can determine the velocity, not just the distance. Understood? So this is what happens. So you search for the correlation peak, and that is exactly what happens. This is also, we covered it in great details in the lecture. So the idea is to do the Fourier transform, multiply get the power spectrum and the power spectral density, then do an inverse Fourier transform, and then search for the peak. And the peak should be located at some distance from the center. So this, once you locate it, you know what is going to be your displacement, and hence you know the velocity. So very small displacements can be measured. So now we look at some of the PIV demonstrations, and this comes from my lab mostly, and then a little bit from L. Venkatkrishnan's lab at NAL also. So this is, for example, what we did over here. I will give you some examples across scales. This is, for example, a millimeter sized bubble, and we are trying, and this bubble is being inflated. Okay, this bubble is being inflated, like you blow a bubble essentially. So we are trying to see what happens to the flow field inside this soap bubble. Okay, so to determine the internal dynamics, we perform PIV measurements. Okay, so as we know, this is the me scattering images if you look at it. Okay, so these are the me scattering images. You can see the, this is strongly seeded, so you can see the flow structures. Okay, you can see the toroidal vortex. You see the flow is actually rotating here. Okay, and here you can see the corresponding vorticity. This is determined from these flow structure images, and you can see those lines. Those are the velocity vectors. Okay, so you see the vorticity and the velocity both in this kind of an experiment, and this is within a several millimeter sized bubble. Okay, it's pretty large actually, but still pretty small. That it is within the bubble. Remember, this is the flow within the bubble, not outside the bubble. So so this, you can see that this is a time resolved PIV. That means you are basically doing it at high speed, but the idea is still the same. You can measure the velocity field and you can measure the vorticity field once you know the velocity at each point. And then of course, we also see examples that how the flow structure, just a qualitative visualization will also give you an idea what is the flow structure inside this. Okay, so this is an example where you have done the PIV in very complex geometries. Okay, so you can see this is the vorticity data, and then you can do all kinds of mathematical wrangling on the data. Okay, so this is to identify, the LIC is to identify the structures, okay, from the PIV data. This is vorticity from the PIV data. As you know, vorticity is this. Okay, so all these things we have done during the soap bubble inflation experiment. So this is complicated. Okay, and this is one level above, so that I showed it for millimeter. Now what about we go actually to meters? This is the flow within an actual gas turbine. So you can see this is a 20-degree sector of a modern annular gas turbine combustor with optical axis to withstand 20 bars of pressure. So one needs to see the flow field inside this combustor. You can see this is the combustor that is used for power generation, and also in your aviation. The aircraft has these combustors, for example. Okay, so you need to see the flow inside this combustor. So the motivation is pretty simple: to probe into the various global parameters into this real scale gas turbine combustor and predict their evolution as a function of the corresponding local event interactions. All right. So this is a 20-degree sector combustor with optical axis built to withstand 20 bars of pressure. And this is high fidelity flow data, which is done through high speed PIV. So you can see this is the high-speed PIV, which actually shows the, the vector field, and at the background you have the vorticity field. So you can see it is a very fast measurement as well as pretty complex to begin with. So this is and this is done over a scale which is much larger than the bubble that we said. So this shows that how PIV can be used, for any system, small scale or large scale. And here you can see, if you take this data and if you average, you get these beautiful flow structures. So this is like an averaging over time that you get. And remember, here you have all those perspective distortions and other type of stuff, because you may not be at exactly 90 degrees with respect to the flow. This is another thing that we did. This is high shear injector. This is a new class of injectors which are to be used in the AMCA combustors. So this is with this comes with this is a multi-phase system now. So it comes with you have to do not only flow field but also droplet sizing, which kind of reminisces of PDPA and other types of measurements. So you can obtain very high fidelity PIV data for characterization of average flow field. So you can see that this is the kind of time averaged flow field data that you get. Okay, so this is 1, 2, 3, 4. So these are at the different flow conditions. Let's not focus on what are those, but you can see this spectacular, flow field patterns, and these are again colored with vorticity. But you can see the, the the arrowheads, which shows the PIV. Okay, and this is of course complex, interactions of the droplet in a swirling flow field. So you can see this is how the droplet actually interacts with the flow field. Okay, so this is an example of droplet flow interactions, and these are some of the other things. These are all videos which basically shows that how the droplets are dispersed by the flow field. So there is the flow field, and you have also the droplets coming and injecting on the flow field. And this is the arrangement of the PIV. Once again, here, of course, we use a laser guide arm because the laser is located somewhere else. And then again, we create a sheet, and then we observe this flow field in the presence of large droplets. And you can monitor the droplet as well as you can monitor the flow field. So this is brilliant. Okay. And also we have done work on this kind of vortex rings, for example. This is a vortex ring formation and interaction with different substrates, specifically in the context of vortex cleaning. So this is interaction of the vortex with the porous media. You can see the intricate flow structures at different Reynolds number combinations. So all these things have been done in our lab. This is from Venkat Krishnan's work, which shows phase-locked 2D PIV measurements. So this PIV measurements, because it is phase locked, that means at certain angles only it will take the measurements, and because it is situated in an oscillating aerofoil and with an AC motor. So this is the kind of stuff that we have that NAL has done. This is the mean flow features over the aerofoil, and there are dynamic features also. So you can see it is velocity is about 28 meters per second. This is phase locked measurements over 2D measurements on a cylinder. So you can see actually what is the rate of vortex shedding. Okay, and this is the kind of experimental setup. Here's hot wear anemometry is also used as a probe measurement at a particular location. So you can see that all these things are done again by the YAG laser and the delay and the bandpass filter. So all these things are features that we have covered already. These are some of the phase averaged measurements, which is at 180 degree and which is at 0 degree with respect to the reflective symmetry in x-axis. These are the phase averaged measurements, more on the phase averaged measurements. So Schumflug connections we have also covered. This is for stereo. This is when it is looking at straight and when there is perspective distortion. Schumflug connection, actually, where the object plane, the lens plane, and the image plane all coincide at a particular line. This is the line, so it looks like a point in the other projection. So this has got two angles, the theta 0 where the lens is placed and the imager is placed at a slightly different angle with respect to this. This is Schumflug condition. And you can read about it more from the internet or from any other book. We also covered it in a little bit of details in our PIV lectures. This is how the calibration process is carried out. So what happens in the case of stereo PIV, the images of the target are recorded. Then the target contains calibration marks. So comparing the known mark position with the corresponding marker, we adjust the model parameters to give the best possible fit. So this is how perspective distortion actually happens. So stereo PIV, these are stereo PIV measurements on delta wing. You can see the Schumflug connection. This is the optical axis. The camera is located at a slight angle. So this is how the measurement is actually carried out. And this is the measurement of the different planes at different flow conditions. This is stereo PIV measurements actually. Okay, this is more stereo PIV measurements on the delta wing at low speeds. Okay, this is PIV measurements of an air blast atomizer, which is basically the kind of similar type of atomizers that we showed earlier in our measurements as well. So for uncertainty and error, we will spend a minute or two. So the uncertainty stems from errors. The uncertainty can be many things. largely considered as the distribution of error, which is assumed to be Gaussian, but it could be something else also. So there are random error sources, like for example, low seeding densities, then mean out of plane motion, then shot to shot variation of laser sheet, misalignment, background noise, very strong shear, so particles are not able to flow. Then bias errors like scaling error, timing error, peak locking error, all these errors leads to uncertainty in the PIV measurements. So it is a non-trivial task. You can see there is data acquisition, there is velocity estimation, there is physics, which is the fluid mechanics essentially. So, and you have the flow field, physical system, flow tracers, illumination, imaging, image analysis, data validation, data reduction. And then there are issues. We have optical access issues, we have space and time and space scales, we have non-uniformity issues, we have velocity estimation issues, we have outlier detection, derived statistics, etc. And these all leads to error sources in shear, distortions, resolution issues, filtering issues, correlation issues. All these issues comes into the picture. This is taken from the LaVision, and this shows that this is a non-trivial task indeed. Okay. So there are many references, as we already have covered this in many details, mainly from this book. Okay. There are other books, other kind of things that are there also available. We have taken a lot of things from our own work. So I think this is where we end the PIV lectures completely. And thank you.